Hello everyone, and welcome back to our introductory course on quantum computing. Today, we'll be talking about one of the three quantum mechanical phenomena that help quantum computers gain a quantum advantage, superposition. So first, let's talk about some of the basics of superposition. Firstly, superposition is the third state that quantum computers can be in, the first two of which being the state 0 and 1. When a qubit is measured in superposition, the qubit will collapse into a state of 0 or 1, and this probability is variable depending on the quantum state. And finally, multiple qubits can be put in superposition at the same time, and this is how many quantum algorithms start in order to provide quantum advantage. Now, superposition can be quite a hard concept to grasp at first. So let's take one good example of superposition, which is Schrödinger's cat. So for those who don't know, Schrödinger's cat is created by placing a cat in a box and placing basically a vat of poison inside the box as well. At some random time, the vat of poison will poison the cat and kill it. However, before we open the box, we do not know whether the cat is dead or alive. This is basically what we call superposition. The cat is in superposition because we don't know what state it actually will collapse into. But then, when the box is opened and we peer inside, we will know whether the cat is dead or alive, and this is like measuring a 0 or 1 state in quantum computers. One superposition-specific term to cover is uniform superposition. Uniform superposition is simply where a quantum state has an equal chance of collapsing into each separate state. So above, we can see that in both cases, I have a 50-50 chance of landing in the 0 state and the 1 state. However, this can also be applied to multiple qubits where, say, you had 4 states that the quantum state could collapse into, then each state would have to have a 25% chance of being collapsed into when measured. Now, you might be wondering how we actually create superposition on a quantum computer. In all quantum computers and quantum circuits, superposition is created using the Hadamard gate. Then this superposition state can be manipulated using other single qubit quantum gates, which we will cover in the next lecture. So here is the matrix representation of the Hadamard gate. We can see that in front, we multiply the matrix by a scalar of 1 over root 2. And inside the matrix, we have 1 and 1 on the top row and 1 and negative 1 on the bottom row. So the Hadamard gate can also be represented as 1 over root 2 and 1 over root 2 on the top row, and 1 over root 2 and negative 1 over root 2 on the bottom row. So what does the Hadamard gate actually do? As a reminder, the Hadamard gate puts a single qubit into superposition, but what type of superposition the qubit goes to depends on its initial state. So when we apply a Hadamard gate to the 0 state, we get 1 over root 2 ket 0 plus 1 over root 2 ket 1. And this is also known as the plus state. However, when we apply a Hadamard gate to the 1 state, we end up with the quantum state of 1 over root 2 ket 0 minus 1 over root 2 ket 1. And this is also known as the minus state. These states are slightly different as we can represent them on the block sphere. When the plus state is on the block sphere, we can represent it as the furthest spot to the right on the sphere, while the minus state is the furthest spot to the left on the sphere. So let's take a look at how the Hadamard gate is actually applied to quantum states. So in this example, we will apply the Hadamard gate to the 0 state. So here we can see the Hadamard gate on the left times the 0 state, which is 1 on the top and 0 on the bottom. Now this, when multiplied out, equals the scalar on the outside, and on the inside we have 1 times 1 plus 1 times 0 on the top, and 1 times 1 plus 1 times negative 1 times 0 on the bottom. When you add these values together, you get 1 over root 2 on the outside as a scalar, times 1 on the top and 1 on the bottom. Now, when multiplying the scalar out, we get 1 over root 2 on top and 1 over root 2 on bottom. And from the last lecture, we learned that The top value squared is the probability of collapsing into the 0 state, and the bottom value squared is the probability of collapsing into the 1 state. So we know that we have a 1/2 chance of collapsing into the 0 state and a 1/2 chance of collapsing into the 1 state. Now in example 2, let's take a look at what happens when we apply the Hadamard gate to a single qubit in the 1 state. So as in the previous example, we first have the Hadamard gate matrix representation of 1 over root 2 as a scalar times the matrix representing the Hadamard gate. Now this is multiplied by the matrix representation of the 1 state, which, as a reminder, is 0 on top and 1 on the bottom. Now when multiplying this out, you will get still the scalar value of 1 over root 2 on the outside, and on the inside we will have 1 times 0 on the top plus 1 times 1, and on the bottom we will have 1 times 0 plus negative 1 times 1. Adding these values together, we get 1 over root 2 on the outside times 1 on the top and negative 1 on the bottom. When we multiply the scalar value in, we get 1 over root 2 on top and negative 1 over root 2 on the bottom. And as we learned on the last slide, this is also called the minus state. One final thing about the Hadamard gate is that when we apply 2 Hadamard gates in a row to a qubit, we end up with the initial state. So for example, if we started out with the 0 state and then we applied a Hadamard gate to it, we'd end up with the plus state. And then if we applied a Hadamard gate to the plus state, then we'd end up back with the 0 state. And this is the same thing if we start in state 1. If we start in state 1, then after applying a Hadamard gate, we'll be in the minus state. And then after applying another Hadamard gate to the minus state, we'll end up back in the 1 state. So what really is the significance of superposition in quantum computers? Firstly, superposition allows us to be in 2 states at once, basically. And therefore, this allows us to store 2 states in 1 qubit, or 4 states in 2 qubits, and etc. This means that as the amount of qubits increases, the amount of states we can store increases exponentially as well. However, as I mentioned in the first lecture, in classical bits, the amount of data we can store increases linearly with the amount of bits or transistors we have. This lecture, we covered superposition and the Hadamard gate, which is one of the single qubit gates used in quantum computers. However, there are 3 more single qubit quantum gates, which we call Pauli operators, and we'll be covering these in the next lecture. Take care, everyone.